Hey, IB Physics kids, welcome back. And this is Thermal Physics 3.1 Thermal Concepts. And we're going to break this into two parts. So, this is part one. So, Thermal Physics part one. A lot of this should be review. And if you were good at chemistry, this will be really, really easy. If you're not good at chemistry or you haven't taken chemistry, this might be a bit of a struggle for you. And that's okay. You'll just have to look at the extra resources, and I'll try to point those out to you later on, and I will definitely point those out to you in class. Okay, so part one. All right, basically, there's this idea of pure substances. Pure substances can be an element or a compound. Elements are made up of atoms, which can become molecules, and compounds are either molecules or ions. And these are all things that you need to understand. These aren't mixtures, they're pure substances. Okay, so what is a mole? Okay, you can click this link in your master notes on your notes on Schoology, or I got it all queued up for you. It's only 4 minutes, so we're going to watch it together here.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now, the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole, this mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1,000,000 a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
All right. So hopefully that gives you a little refresher to what a actual mole is. Some people have a really hard time with that, and that's okay. It's not that easy. If it was that easy, everybody would talk about it. So again, what is a mole? Okay. Uh, and I kind of have this written out to you. It's basically everything that was just in that video. But the thing is, you got to remember in physics, we denote Avogadro's number or its constant by capital N with a capital A subscript. So it's like number Avogadro. Okay, so number Avogadro. All right, how do you convert? How do you convert, which is something you're going to have to do in here. All right, you are welcome to click on this link if you need help with that. It will walk you through how to calculate and convert everything that you need to do. And also, um, it will be also in the resources folder. Okay. I always remember my chemistry teacher had this up on his wall. Chem is try, not chem is hard. Okay. So remember that. All right. And I have some other resources for you to look at as well. So feel free to click on that link in the master notes as well. Some of you are going, I got it. And that's fine. And you don't need to do any extra work on that. Okay. So basically, moles are in kilograms per mole. So example, if the molar mass of oxygen is 15.99 grams per mole, okay, this is called a molar, the molar chart, okay? And you can look at this. If you're given something in grams and you want to convert it to moles, you follow this process. If you're in moles and want to go to gram, you follow this process, okay? It's something that we used at Scioto, and you're welcome to use that if you want. So the molar mass of oxygen gas is 32 times 10 to the negative 3. Okay, if you have 20 grams of oxygen, how many moles of it do you have? Well, you take that and you convert it to grams. Okay, and you do a little division there. Excuse me, you take the grams and you convert it to kilograms, is what they did. And then they divide it and they find out there's that many moles. Once you know that many moles, you can multiply it by Avogadro's number and you get how many molecules there are. And that's kind of the process that we use a lot in physics. Once we have the mass of something, we can divide it by its molar mass, get its moles, multiply it by Avogadro's number to tell us how many actual particles are being used. Okay. And, here's an example, another one, again, worked out for you. Again, IB loves to use these conversions to mess you up, to be honest. It's not that big of a deal. You'll be fine. We'll work through it. All right, 3 states of matter. We're going to go through this pretty fast. This should be a review. You've probably heard these since all the way back to 6th, 7th grade. Solid, liquid, gas, and plasma. We obviously have to add heat as we rise to that. Again, as we move through our 3 major parts of matter, we tend to know that there's more disorder. It's called entropy, so forth and so on. All right, so what about energy? Internal energy. Now, internal energy, we always think of like chi, okay? This idea of what's inside of you, or this energy inside of you. Well, there's this thing between internal energy and heat, okay? Internal energy is the energy of a body that is the total energy associated with the thermal motion of the particles. Okay, we'll talk about this more. It comprises both of kinetic and potential energies associated with the particle motion. As kinetic energy rises, it then subtracts from the potential, but the rotational motions of that substance. Potential energy arises from the forces between the molecules. Okay. So, for example, internal energy, you need to think about this. If I heat up a metal bar and then I put the metal bar to the side, is it still hot? Well, of course it is. Okay, because the particles inside are moving rapidly. They have internal energy, just like an ice cube. You don't put ice cube out in 100-degree weather from your refrigerator and it melts instantaneously. It takes time. Okay. When your car slows down using its brakes, kinetic energy will be converted into internal energy into the brake pads and disc. We know about friction, obviously, but at the same time, as those things are moving, they're heating up and the internal energy gets faster. they'll say in racing, they'll tell you to warm up your tires, but you may also notice at the farther you drive in the snow, you'll notice the car tends to grip better. Okay. And that's because the wheels are actually warming up the road and so forth and so on. So temperature, at the microscopic level, temperature is the degree of hotness or coldness, if you will, measured by a thermometer. Okay. It is the average kinetic energy of an object. Temperature in Kelvin, if you don't remember Kelvin, you just take the temperature in Celsius and add 273 degrees. Okay. When a temperature of Kelvin is 0 degrees Kelvin is called something, it is called absolute zero. Okay. So just looking at it's the same gradient, but notice 0 degree Kelvin is the same as negative 273, or think about it as 273 degrees Kelvin is 0 degrees Celsius, whichever. Okay. Again, 0 degrees Kelvin is negative 273 degrees Celsius. That's absolute zero. That is the theoretically known point where all matter ceases to move. It's frozen, if you will. So in a weird world, if we were able to go absolute zero on anything, we'd be able to, like with a table. If for some reason you could protect your body, but the table in front of you went to absolute zero, you could all the particles in the table would stop moving and vibrating. So technically, you could like move your hand through the table or separate the particles for them to move, and you could literally transport yourself through that table. Again, here's a little conversion. Again, if you feel overwhelmed by this, well, technically, we are the only country now that uses Fahrenheit. Everyone else uses Celsius. A couple of our territories too, but we are the only official country to use Fahrenheit. Okay, you guys should know what thermometers are, everything like that. Again, being able to read the scales, the difference between Celsius, Fahrenheit, and Kelvin. All right. Again, temperature, average kinetic energy of the molecules. Again, hot particles should move faster than cooler particles. Here you go. Here's one of the most important slides: temperature and heat. Temperature. A body's temperature is due to the vibrational kinetic energy the particles have. So, how hot it is. But heat, a body's heat, is due to the number of particles the kinetic energy of that object has. Okay? So, that's important. It is important for you to understand that the temperature of something might not be the same as how much heat it's producing. What does that mean? Well, let's just say like normal fire. Normal fire is like 500 degrees Fahrenheit. Okay? Well, if it's 500 degrees Fahrenheit, one flame is 500 degrees. But a bonfire is still 500 degrees. But which one produces more heat? A little lighter, one flame, or a giant bonfire? Well, obviously, the bonfire. Let me use a different example. What if I heated up a cup of water? Well, let's make it boiling. Let's make it 100 degrees, 100 degrees Celsius. But let's say I have a cup of water and you put your hand around that cup of water. It's 100 degrees Celsius. It's boiling. You might burn your hand. Well, what if I heated up an entire bathtub to 100 degrees Celsius and had a boiling bathtub? Which one's going to produce more heat? Well, the bathtub. But which one has which one has a greater temperature? Neither. They have the same temperature. They're 100 degrees. Hopefully that'll make sense. Again, heat is the thermal energy absorbed or given or transferred. Okay. And this always occurs from a higher to lower temperatures. Okay. Cold does not win with the heat. The heat travels to the cold. Okay. So again, they're always going to flow from hot to cold to equal what we call thermal equilibrium. So over here to the right, these are going to equal thermal equilibrium. If the density and the masses of these two objects are the same, what would be their thermal equilibrium? The answer, 275. Right? Again, notice right there, they're going to transfer 0 and 100 degrees, bring them together. Eventually, they're both going to equal 50 degrees Celsius. Okay, if you need to remember how to understand or what the difference between these three things are, conduction, convection, and radiation, then you can go to this simple little link here in their master notes and watch that. Again, that's just for your review in case you don't know what those terms are. A real quick crash course. Conduction, you must have contact for conduction. This is like a metal spoon in boiling water. That's why the end of the spoon gets really hot, even though it's not touching the heat source, through conduction, through contact. Convection, hot air rises, cold air falls. You put your hand down here and it won't get burned. Put your hands up here, they can get burned because hot air rises, cold air falls. And then radiation. Radiation moves in straight lines away from this. Okay, that's why the part of the earth that's facing the sun is always going to be warmer than the part away. No matter what, the temperature will always go up in the day versus the nighttime. Also, a great example is if you've ever been to a bonfire and you've sat around there, your knees are probably facing the fire. Your knees sometimes get really, really hot. The front of your pants get really, really hot. But people wear blankets and stuff because their backside or the back of their legs might be freezing. So you see a lot of people stand up and turn around sometimes, okay, to try to warm up the other side because it's traveling in a radiation. Okay. There are your homework problems for this section. I know this is a little long. Part 2 is a little long, but some of these notes are a little long. We're covering a lot of material. All right. We'll talk to you soon. Thanks for watching and good luck to you.